Hello everybody, and welcome to exercise 1 on page 48 of the workbook. And this is going to be our first example of actually using the chain rule to find a derivative using specific formulas. Okay, so taking a look at the problem itself here, they'd like us to find dz dt, the rate of change of z with respect to t, given that z is equal to x e to the y, and x and y are functions of t given as follows. Okay, and so I'm going to use a similar approach to what we used in the preliminary example, starting with the dependence diagram here. So we've got our z that we're trying to find the derivative of, and we'd ask the question, what variables is z a function of? Well, we can see from our formula here that it's a function of x and y. Okay, and then we would ask, what about x and y? What are they functions of? Okay, well, you can see from these two formulas that x and y are just functions of t, both. Okay, so we'll draw it that way. And that diagram is useful for us because it kind of gives us a roadmap to writing down a formula for dz dt. So what we're going to do is to ask ourselves, how many paths are there in that tree from z to t? Okay, well, there's one over here, taking z through x and then x to t. And so if we just take derivatives along each step of our path, we're going from z to x, that's going to be partial z partial x. And then we're going from x to t, that's going to be dx dt, okay, which takes care of the first path. But there's another path from z to t over here. And along that path, we're going to go from z to y, so that's partial z partial y. And then we're going to go from y to t, which is dy dt. Okay, and there's our chain rule formula for dz dt. And now we just have to do the calculations and see what we end up with. Okay, so starting with dz dx, okay, here's our formula for z. So what would the partial derivative of that be with respect to x? Well, let's see. The derivative of x is 1, and then the e to the y is going to come along for the ride. Okay, next thing we come to is dx dt. Okay, when you take the derivative of x, with respect to t, you're going to get 2. Okay, and continuing over, partial z partial y, that's taking us back to the original function. And when we take the derivative with respect to y, x is going to come along for the ride. The derivative of e to the y is still e to the y. And then we need to multiply by dy dt. Okay, and you take the derivative of y with respect to t, you're just going to get minus 2t. Okay, that would qualify as an answer. If you wanted to, you could also go one step farther and say, let's write our answer as a function of t. All right, so for example, we could go back and say, what is this y equal to in terms of t? Well, we can see from up here that y is 1 minus t squared, so we could write this as e to the 1 minus t squared times 2. Okay, and then similarly, the x e to the y that you see if you fill in what x and y are equal to. Okay, this is getting a little cluttered. Let's erase a little bit. So x is 2t and y is 1 minus t squared. If we fill those in, okay, we get that. Okay, and that's just another way of writing our answer that we have here. Okay, one comment that I'd like to make. Could we have done this problem without the chain rule? That's an interesting question. Okay, it turns out that the answer to that is yes. Okay, because if you go back to the very first step of this, z equals x e to the y, we can use the values of x and y that were given to write z as a function of t at the very first step. Okay, in other words, let's say it this way. Z is equal to x e to the y. If we fill in immediately what the x and the y are, we're going to get 2t e to the 1 minus t squared. And we can take the derivative of that just using ordinary calculus 1 rules. Okay, so here we'd be taking the derivative of this using the product rule, and we'd get 2t e to the 1 minus 2t squared times negative 2t. Okay, that's the first times the derivative of the second plus the second times the derivative of the first. Okay, and you can double check and just confirm that these two answers are the same. Okay, so think of what we did down here as a check. This is an alternate solution to the problem that we did above.